Hi, this is Calculus 2, Math 2020, and this is lecture number 37. And we will be talking about section 11.7. It's a very short section with lots of exercises. And this will be we'll be mostly just doing exercises today. Okay. So section 11.7 is strategy for testing infinite series. I do this similarly to the book, but I make one change because and the one change is actually at the very beginning. So suppose you're given a series, summation a sub n. So you want to know, does it diverge or does it converge? So that's really the basic question. And what is the strategy when presented with a series? What do you do? Well, here are some options, okay? So the first thing I would suggest is look at the terms a sub n. If you can see easily that the limit as n goes to infinity a sub n is not 0, then the series diverges by the divergence test. So I often look at that as a first check, okay? But most series will have the property that the limit is of the terms a sub n is 0, in which case the divergence test fails to apply. It's inconclusive. So you're going to have to use one of the other tests. Okay, so now the question is, how do we try to deal with this? Well, first of all, is the series a p-series? You could ask. Well, we know that if it's a p-series where p is strictly greater than 1, it converges. And if it's less than 1, it will diverge. So if your series is a p-series, we know what to do. Is it a geometric series? Well, if it's geometric and the common ratio has absolute value strictly less than 1, it will converge. So now we start getting interesting here. What if is it similar? Is it in some way similar to a p-series or a geometric series? Well, then you may want to consider one of the comparison tests, maybe the comparison test, assuming the series has non-negative terms, or maybe the limit comparison test may be useful. There's no guarantee it will be useful, but one can always try. Okay, so now, so then next thing is it alternating? Then maybe the alternating series test will work. Well, what happens? What happens left? Well, what if a sub n is a product of things, or maybe there's a factorial in it, or maybe there's some power in it. Well, maybe the ratio test, or maybe the root test, depending upon the situation, will help. Okay, and lastly, if a sub n is the value of a function f of n, where the function is not negative and decreasing, then maybe the integral test might help. So this is the strategy, more or less the book strategy too, except I just changed things around a little bit. So I think what is most useful is just to do a lot of examples. And since the examples are not pigeonholed into a section that came before, you're going to have to use some intuition and ingenuity to figure out what to do. So that's the idea. Okay, so now let's proceed with that. Okay, so I'm going to use something. All of my examples will come from the exercises in this section. So summation n squared minus 1 over n cubed plus 1. N goes from 1 to infinity. So that's this is example 1. Well, this is looking like n squared minus 1 over n cubed plus 1 seems to be related to 1 over n. And unfortunately, the comparison test won't work here. By the way, the divergence test clearly, the limit of a sub n, this is a sub n, is going to be 0. So that the divergence test won't work. The comparison test is not going to work because n squared minus 1 over n cubed plus 1 is not less than or equal to 1 over n. It's the other way around. Well, it's just not going to work. And 1 over n is divergent, so it's not going to help. So we have to do, maybe the limit comparison test will work. So what I'm going to do is I'm going to do a limit comparison between n squared minus 1 over n cubed plus 1 and 1 over n. So I'm going to take n squared, this is my a sub n, and this is my b sub n. So a sub n over b sub n, these are series with non-negative terms, is given by n squared minus 1 over n cubed plus 1 times the reciprocal of b sub n, which is n. So what do we get? This is the same thing as n cubed minus n over n cubed plus 1. And this will tend to 1 as n goes to infinity. Well, that tells us that the test is inconclusive. Okay, so that's not going to be so good. What other options are there? Well, we could use maybe the ratio test, or maybe the integral test are left, right? So let's try the integral test. So f of x equals x squared minus 1 over x cubed plus 1. And this is a decreasing function. You can check that by taking the derivative. So this is decreasing and non-negative. So let's figure out whether the integral of x squared minus 1 over x cubed plus 1 exists. By the way, if you want to get full credit on an exam with a problem like this, you'd have to show using some method or another that the function's decreasing. You could use calculus to check that. So anyway, let's check what the integral from 1 to infinity of x cubed plus 1, x squared minus 1 over x cubed plus 1 is. Does it converge or not? Okay. Okay, so let's see. I retract what I just did. So let's not try to calculate this integral. I'm going to go back. I did not apply the limit comparison test correctly. Remember what the limit comparison test says. If you get this is C, and C is a finite number, then either both series converge or both series diverge. Well, summation 1 over n, which is the harmonic series, diverges. So summation n squared minus 1 over n cubed plus 1 diverges. So we were on the right track. I just didn't apply the test correctly. So this is why it works. So we use the limit comparison test in this case, and this turned out to work well. Okay, so so there we go. Let's go to the next problem. So what about the summation e to the n over n squared? N goes from 1 to infinity. Now I can stare at this and see that a sub n is e to the n over n squared. And this, it looks like the numerator is blowing up much more quickly than the denominator is. So I would guess that the divergence test is going to work here. So let's check the divergence test here. So the limit as n goes to infinity of e to the n over n squared, I'm going to rewrite that as a limit as variable x goes to infinity, e to the x over x squared. And this is an indeterminate form in the sense of L'Hopital's rule of type infinity over infinity. And so the limit as x goes to infinity of the quotient e to the x over x squared is the same as the limit as x goes to infinity of the derivative of e to the x, which is e to the x, divided by the derivative of x squared, which is 2x. Now, this limit also is a limit of an indeterminate form of type infinity over infinity. So we can do L'Hopital's rule a second time. So that would be the limit as x goes to infinity of e to the x over 2. Now, as x goes to infinity, this fraction blows up. It goes to plus infinity. So therefore, the divergence test applies. The limit is not 0. It should have been 0. So the series diverges. So the answer to example 2 is the series is divergent. So let's do example 3 now that I want to do. Summation 3 to the n squared over n factorial. Okay, so n goes from, say, 1 to infinity. So this is a product, and there's a factorial here. So the suggestion is to use the ratio test. Let's try it. So this is, what does the ratio test say? We have to take absolute value of an plus 1 over a sub n and take its limit. So let's look at that. Let's look at that quotient. So that's 3 to the n plus first power times n plus 1 squared over n plus 1 factorial. That's a sub n plus 1. Dividing by an is the same as multiplying by the reciprocal of an. So that's n factorial over 3 to the n times n squared. Now we can do some rewriting here, some cancellations occur. The 3 to the n plus 1 over the 3 to the n is a 3. We have n plus 1 squared on the top. The n factorial and the n plus 1 factorial cancel out to leave an n plus 1. And we have an n squared on the bottom. And now what is this fraction? Well, there's more cancellation. This is 3 times n plus 1 over n squared. Now what happens to the limit as n approaches infinity? Well, this is, let's rewrite this as 3n plus 1 over n squared, which is the same as 3 over n plus 1 over n squared. And this tends to 0 as n goes to infinity. So the ratio is actually 0. Hence, the ratio tends to 0. So therefore, the ratio test, since 0 is less than 1, implies the series converges. So this series converges. Okay, let's go to another problem. Okay, so summation sine 2n. This is a weird series, sine 2n over 1 plus 2 to the n. Now this series has neither positive, is not a series of positive terms. Let's say n goes from 1 to infinity. It's not a series of positive terms. There are not too many tests that we can apply to a series which is not of positive terms. there are some cases where the sign will have a negative value. So what the idea is I'm going to do is I want to show that the series, let's check for absolute convergence instead. In other words, we're going to be looking at the series n goes from 1 to infinity of the absolute value of the sine to n over 1 plus 2 to the n. So now I'm gonna like, let me write down a sub n. That's absolute value of sine 2n over 1 plus 2 to the n. Now the sine function is always less than or equal to 1, so this is less than or equal to 1 over 1 plus 2 to the n. And this series this is also greater than or equal to 0. So I'm going to and we can do better than this. We can even make this less than 1 over 2 to the n, because summation 1 over 2 to the n is geometric with common ratio 1/2, so this will converge. So I'm going to use the comparison test. So now, so therefore, the comparison test then implies that the summation of the absolute values converges because our geometric series converges. Okay, so the series absolutely converges. So this so that's what we needed to know. It absolutely converges. In particular, it converges because absolute convergence implies convergence. Okay. So let's try the following example. The sum n goes from 2 to infinity of 1 over n times the square root of ln of n. All right. So I look at this and I say, aha, there's not much we can compare this to, so we're not going to use any comparison test. We could try the ratio test, but I think the easiest thing is going to be the integral test. So we want to look at the function 1 over x times the square root of ln of x. Now this is clearly decreasing. It's a decreasing function, and we can consider the integral from, say, 2 to infinity of dx over x times the square root of ln of x. So it's an improper integral. If we can show this converges, then our original series will converge. Okay, so now the way to do this is to let u equal ln of x. Du is 1 over x dx. So then this integral that we're trying to compute, so when x is 2, u is ln of 2. And when x goes up to infinity, ln of infinity of some very large number is very large, u is going to be infinity. So then we have du, which is dx over x. So you get du over the square root of u. In other words, the integral from ln of 2 to infinity of u to the minus 1/2 du. Okay, so now we find the antiderivative. That would be u to the 1/2 power times 2. And u is going from ln of 2 to u equals infinity. Let me write it, just ln of 2 to infinity. I should really be writing a limit, but I'm just going to write ln of 2 to infinity. Now the problem with this is when you stick in infinity into u to the 1/2, it blows up. So this is going to be plus infinity. So it diverges. So therefore so this series diverges by the integral test. Okay. Okay, so now for our next problem, I think this is number 6. I want to look at the summation n factorial over e to the n squared. So there's a factorial here, and the suggestion is to use the ratio test. So what does that tell us? We want to take n plus 1 over a sub n absolute value. So that's n plus 1 factorial over e to the n plus 1 quantity squared times the reciprocal of a sub n, that would be e to the n squared divided by n factorial. And now we play games with algebra. So n plus 1 factorial over n factorial is n plus 1. E to the n plus 1 squared. So this is time. So this the two e exponential terms becomes e to the n plus 1 squared minus n squared. So that would be n plus 1 over e. So n plus 1 squared is n squared plus 2n plus 1. So we're subtracting off n squared, so you get e to the 2n plus 1. Now what happens as n goes to infinity? As n goes to infinity, we have L'Hopital's rule. We can apply L'Hopital's rule as n goes to infinity, and we could be looking at the function e to x plus 1 over e to the 2x plus 1. If you do L'Hopital's rule, the limit as x goes to infinity of that expression is the same as the limit as x goes to infinity of 1 over 2 e to the 2x plus 1, and that's going to be 0. So therefore, the limit in question is 0. And what does that tell me? Well, the ratio test tells me, therefore, that the series converges by the ratio test. Okay, I think we should do one more problem today. So let's try this one. Summation 5 to the power of k over 3 to the power of k plus 4 to the power of k. Now, there are various ways to try to think about this. It took me a while to see the trick here. I think we could just rewrite this a sub k in the following way. We multiply both top and bottom by 5 to the minus k. That's like multiplying by 1. So the numerator becomes 1, and the denominator becomes 3/5 to the k plus 4/5 to the k. Now, if you have a number that's less than 1, strictly less than 1, and you keep raising it to a higher and higher power, that number gets closer and closer to 0. For example, take a half. If you raise a half to the billionth power, that's 1 over 2 to the billion. That's very small. If you raise, so it's getting closer and closer to 0. So the denominator here, each term is going to 0. And since the denominator is going to 0, its reciprocal is tending to plus infinity. So the divergence test implies the original series diverges. And there you got it. That's it for today. We've gone through strategy. We've looked at different series. And the only way to get good at this is to practice. Cheers.